It's a sincere pleasure to introduce Tiffany Cheng, who is also our inaugural tenure-track faculty member in Design Tech. We're so excited to have Tiffany here officially, joining as of January. So a bit about Tiffany. Tiffany is a Taiwanese-American designer, builder, and assistant professor here in Design Tech. Her work examines the performance potential of natural and bio-based materials for smarter and more sustainable forms of making. I had the pleasure of getting to know Tiffany and her work while I was on sabbatical in the fall of 2023 as a visiting professor at the Cluster of Excellence at the University of Stuttgart, where she was very generous with myself and my students in sharing her work that was just about to be defended as part of her doctoral dissertation. Her doctoral research focuses on developing 4D printing processes to program bio-based materials with bio-inspired behaviors for application domains ranging from self-adjusting wearables and self-forming structures to self-regulating facades. As the former research group leader at the Institute for Computational Design and Construction, led by Akram Menges, Cheng led the material programming research group to investigate integrative computational fabrication methods for creative adaptive furniture and building systems. So she works across scales. Tiffany has also practiced as an architect with Studio Fernando Vasquez, designing socially oriented projects ranging in scope and scale from bike facilities in Southern California to neighborhood recreation centers across the US and Japan. She's also worked at the MAP+S group, the MAPS group at Harvard, GSD, researching material-driven manufacturing strategies for bespoke carbon fiber building components. And this was part of her MDes work at the GSD before starting her PhD at Stuttgart. Tiffany defended her doctorate in engineering at the University of Stuttgart in 2024. And prior to that, she earned her master's in design studies within the track of technology from Harvard, and her Bachelor of Architecture from the University of Southern California. So please join me in welcoming Tiffany. We're very excited to have you joining our faculty. Some of you, I think, are in Tiffany's elective, so the stage is yours.
Thank you so much, Jenny, for the very nice introduction. And I'm super excited to join the Cornell community. As Jenny mentioned, I actually joined a couple of weeks ago, arrived in Ithaca. And before that, I spent 8 years at the University of Stuttgart's Institute for Computational Design and Construction, where I was developing my PhD and leading the material programming research group. I was also teaching in the iTech Masters of Science program. And now here at Cornell University's Department of Design Tech, I'm directing a new research lab called the Multi-Meso Lab, and it aims to advance the performance potential of natural materials for smarter and more sustainable forms of making. I'm also teaching in the Master of Science in Design Technology program. So I want to emphasize the importance of interdisciplinary collaboration in all of my work. So I've worked with partners from material science to physics and biology, as well as industry. And my research and teaching is all about learning from nature on how to use natural materials sustainably and performatively. So this requires the integration of different disciplines. For example, in developing new bio-based materials, in order to turn properties that are normally considered as disadvantages, such as swelling and shrinking, into advantages. Also studying biological role models in order to mimic their structural layering and transfer them using emerging technologies such as 3D printing. And finally, in designing and programming new types of mechanisms whose functions are 100% powered by the environment. So by integrating and synthesizing knowledge from diverse domains, I believe that we can create bio-inspired structures that change shape without consuming any operating energy as an alternative to conventional methods of design and making. Before I go into details of how that works, I want to share a little bit about where I'm coming from. So I've been making things for practically my entire life. I actually built my first 3D printer 15 years ago, roughly. And besides 3D printing, I've also built a huge variety of projects ranging in size from origami robots to large-scale art installations. And having made so much stuff throughout my life, including buildings while I was working as an architect, I became increasingly confronted with the environmental responsibility that comes with the act of making. So this is an infographic comparing in the year 1900 the Earth's biomass on the right and the anthropogenic mass, which is the accumulation of all objects made by humans on the left. And considering that humans only make up a tenth of a percent of all biomass on the planet, since the year 1900, humans, at the anthropogenic mass made by humans has doubled every 20 years. And according to a recent study, this anthropogenic mass has now surpassed the biomass. And in fact, the overall biomass has actually decreased, mainly because of deforestation and environmental degradation caused by our overall manufacturing activities. So this really made me realize that the climate problem is really a problem of making related to how we are using materials. So most of this human-made anthropogenic mass are things like buildings and roads, and manufacturing these construction materials are responsible for 9% of global annual CO2 emissions. Building operations like active heating and air conditioning for maintaining occupant comfort are responsible for 28% of global emissions. So over 2/3 of all carbon emissions are linked to our industrial activities. And so I was thinking, how do we begin to address this global problem? Well, I think that we really need to design our products and buildings to adapt to multiple scenarios, to be used and reused into the future. So the question is, how do we make structures that are adaptive? Well, I think we can look to nature, for one, because nature is incredibly productive. It's silently manufacturing its own goods every second, and it's producing and growing biological materials through abundant material and renewable energy resources. It's fabricating intricate material structures, which are highly performative and also multifunctional. For example, trees can grow over 100 meters while transporting nutrients using minimal material. And those functions can be powered using free energy inputs from the environment, such as the sun. So plant materials can move, changing their shapes and properties in response to the environment through growth and other mechanisms. But I'm particularly interested in the mechanisms of seed dispersal that you can see on the bottom row here, from the folding of pollen grains, the opening of pine cones, to burying seeds and even exploding cucumbers. These are all really interesting, especially because they don't require any active metabolism to function. And the pine cone, I think, really nicely illustrates this principle because its material, its structure, and function are so tightly integrated that it can reliably open its scales without consuming any metabolic energy. And in fact, it's technically a dead tissue when it's disconnected from that living supply of the tree. And indeed, my biologist partners have found that there are even fossilized cones which can still open and close after being roughly 14 million years old. And this is why I love working with biologists. So now taking a closer look at the material structure of the pine cone, we can see how the cellulose microfibrils are arranged in two directional layers. And this bilayer structure is what causes the pine cone to swell or shrink in response to moisture changes. So my goal has been to investigate how we can apply strategies from biology to the design and manufacture of our products and buildings. For example, in building skins that can autonomously provide shading or ventilation depending on the weather. And I even have a hope that one day we can even completely replace conventional heating and air conditioning with more sustainable strategies. So in the next projects, I'll be introducing my previous research in working towards this goal. And fused filament fabrication is especially conducive to emulating that fibrous structure of biological materials for creating these bioinspired and shape-changing systems in a process called 4D printing. So even though printers, 3D printers and materials are really cheap and accessible, one of the core challenges is how do we design for 4D printing, which is a very different paradigm than our current practice of designing static objects and only designing the boundary of those objects. So first I want to explain how 4D printing works is that through the process of extrusion, it leaves these anisotropic features on the material layer, which when you print that with a hygroscopic material like wood filaments, swells or shrinks directionally. And by printing a less swellable layer on top of this existing layer, similar to the pinecone structure that we saw earlier, the resulting bilayer bends in one direction when swelling and the other direction when shrinking. So to develop the tools for 4D printing, my first steps were to explore this principle in a systematic way by programming the extrusion paths with different parameters, such as the spacing and the layer height between those paths. And with that, you can control the bending in different directions, the amount of bending, and even the speed of bending. And by combining and stacking together these different bilayer building blocks, as I call them, you can expand the geometric possibilities. So the mesostructure, which is created by this extrusion process, is kind of like an analog material code that tells the programmed material what shape it should transform into. And in order to understand and verify how such a material's mesostructure reacts to environmental humidity, I printed various permutations of those extrusion parameters and tested them in lab-generated conditions. The results of these experimental data were then used to inform the development of the computational fabrication workflow for configuring an assembly of bilayers within established CAD software like Rhino 3D. And we can preview the shape change of the combined bilayers and then also generate the low-level machine code for creating intricate mesostructures like what you see on the left here. So by integrating material and printing properties into this workflow, designers can then focus on the high-level design without needing to worry about how to organize each and every individual tool path or material path, or needing to learn how to write machine code. And this enables the automated production from the digital design to the physical object and allows for many types of material transformations like bending, expanding, folding, stretching, and even double curvature. So I've already shared these tools with my colleagues and students, and I taught a one-week workshop on 4D printing 2 years ago to bachelor students in architecture at the TU grads. And these are the work of my students. So some of them were quite new to parametric design. Some of them had never used a CAD modeling software coming from more traditional architectural education. But over the course of the 5 days, they were all able to explore their unique ideas in self-shaping design, and I was proud that they could all physically realize them. And so I think this is a very nice litmus test for the accessibility of 4D printing. So the next challenge deals with how to transfer and upscale the methods that I just introduced from hobbyist 3D printers and off-the-shelf filaments to automation platforms and construction materials. So in terms of the materials, wood is a well-known and easily scalable construction material that's very familiar to us. It's also used for self-forming bilayers with high actuation forces, albeit it has a low resolution of programmability. And on the other hand, 3D printing allows for a high resolution of detail in customizing mechanical properties. So in order to combine both of these materials into a hybrid system, I developed a large-scale additive manufacturing platform with multiple end effectors. including an integrated vacuum gripper for the pick and placement of the wood bilayer actuators, as well as a large format extruder for the 3D printing of metamaterial structures to produce this biocomposite structure in which the wood and 3D printing work together to self-shape up to the meter scale. Now, in transitioning from the small-scale 3D printing to the large-scale robot extrusion, it was necessary to make some adjustments in the extrusion toolpaths, which had to be continuous and non-crossing, due to the larger nozzle and delay caused by pressure buildup inside the barrel. So there's a lot that we can do at the small scale that we can't do at the large scale. I also had to recalibrate the 3D printing parameters, although the general relationships between depth, thickness, resolution, aspect ratio, and geometry remained the same. So using geometry, we can then modulate those material properties in specific directions, such as physically programming areas that stretch in certain directions, areas of stiffness, of high stiffness, and also bending, areas of bending in different directions. So this biocomposite structure, just by acclimating its moisture content to the ambient indoor conditions, transformed from the flat fabricated state to a very complex doubly curved shape without any mechanical force or operating energy. And so based on this large-scale additive manufacturing platform that I developed, my master thesis students also explored this using the unique properties of auxetic metamaterials. And what's interesting is when you bend these metamaterial structures, it forms surfaces from positive to negative Gaussian curvatures depending on the pattern, from that hexagon to the inverted hexagon pattern. So they exploited this property of those auxetic patterns and in self-forming bending active shell structures by modulating the pattern to control that variation in double curvature across the shell structure. And from a flat shape, which we fabricated in 13 hours, it formed into this functionally graded shell structure within 1 week. And considering that, the complexity of the shell structure and also the functional gradation of the surface and also that fabrication of the 3D fabrication technology, it's quite fast for such a size. So in the next project, I want to talk about how we can translate working principles from biology to design and engineering applications and vice versa. So this project is a collaboration with the Plant Biomechanics Group and the University Hospital, both at the University of Freiburg. And I use orthotic devices as a motivating example since there's a need for both customization and adaptation for specific patient pathologies. Proper fit is very important for rehabilitation, and indeed 3D printing has become a very popular technique for creating personalized splints. And it's able to work for a variety of shapes and sizes, but this doesn't really address the muscular atrophy that typically results from immobilization. And this is when your limb gets thinner while you're wearing a cast, and that's also the reason why you've had to go to the doctor so often to get your cast refit, if you've ever broken your bone. And the biologists I worked with found interesting this air potato plant, which has a very clever strategy of climbing smooth supports without slipping off. And it generates these high squeezing forces onto the host structure through these stipules that are located on the base of its leaves. And as this plant grows, the stipules expand, and thereby it tensions that stem helix. So we then abstracted and transferred this tensioning mechanism to 4D printing. So the squeezing behavior is set up in two phases. The first, the stem helix loosely winds about its existing structure and then pushes outwards with the stipules in order to stiffen. Then we abstracted the functional principles and interpreted them, the first part as a twisting bilayer strip called the helix mechanism, and the second part as a bilayer flap called the pocket mechanism, which creates a pocket of space between itself and the helix on top of which it sits. And so this is a summary of the biomimetic process. So we take this tensioning strategy from the air potato plant, which was abstracted and then transferred to 4D printing through the design of those two mechanisms. the helix and the pocket. And we can individually tune those mechanisms and combine them into a single material system and evaluate them for applications where the fit and grip are important. So we first tested the 4D printed material system's ability to stay gripping onto a support pole. And here you can see the pure helix mechanism gripping onto a 30 millimeter diameter pole and self-releasing after 40 minutes of moisture uptake. And in comparison, the same helical system, but with pocket mechanisms, was able to adapt the grip for thinner 50 millimeter diameter poles and also stay gripping for well over 3 hours during moisture uptake. And the key was understanding the mechanism that the air potato plant uses in order to generate that force. So we measured the squeezing forces of our 4D printed material system and compared the different combinations of the two mechanisms. So you can see the helix mechanism without any pockets in orange, which generated fairly low forces. Then the addition of those pocket mechanisms in low and high densities was able to generate increased forces to varying degrees. But what was the most effective strategy we found was that by programming a delay in the pocket mechanisms, that was the most effective strategy for increasing the squeezing force. And now the doctors would normally use splints or design splints are not necessarily experts in digital modeling, so we prototyped a design workflow in which physicians could physically prototype those designs directly on the patient's body, 3D scan, and then digitally analyze those curvatures and then generate the fabrication data for 4D printing. And this is really important for adoption outside of the lab. So this is the design of the splint with the Bioinspired mechanism, which self-tightens around the wrist and forearm at varying curvatures. And what's the most important takeaway to me is that we found that we were able to generate a similar range of forces as the air potato plant when we mimic those stipules in low quantities, which is how they are found in nature. And if we increase the number of those stipules and further delayed their actuation using 4D printing, we were actually able to measure higher forces. And so it was really exciting to see that through studying biology and using computational design and material programming, we can actually extend beyond what the plant role model can achieve naturally. So I just want to also say that not only can we take ideas from biology, we can also use 4D printing to better understand biological role models. So for example, this large flowered butterwort, it creates this wool-like depression when triggered by prey. It's carnivorous. And the underlying cellular processes behind this deformation are not really well understood. So this is another collaboration with the plant biomechanics group, and they were very they were curious to use 4D printing to test their various hypotheses. So we used 4D printing to fabricate and test those ideas and try to understand the differentiated cell and tissue layers of the butterwort. And so in general, the approach of reverse biomimetics can help scientists also better understand the biomechanics of new plant role models. So in this last project, I want to address the question I posed in the very beginning of my talk of whether or not we can apply bio-inspired 4D printing to the real world in actual buildings. And so this is another collaboration, another interdisciplinary collaboration with the Cluster of Excellence, LiveMats in Freiburg, as well as the Institute for Plastics Technology at the University of Stuttgart. And the goal here was to adapt the foundational scientific research developed over the past projects I showed to a real building demonstrator application. The new challenges here were on integrating self-shaping design in real buildings, in a real environmental, under real weather conditions across much longer time scales than we are previously used to, and also to scale up 4D printing to the level of a building facade. So we used this LiveMats biomimetic shell building. It was a new project that is now located on the University of Freiburg campus as a case study. And together we designed the self-shaping, the building and the self-shaping adaptive facade according to its specific conditions on the site. So the south-facing orientation of the building made it possible for us to gather the maximum amount of solar heat available. And therefore, in the winter months, we aimed for the 4D printed shading elements to open and allow solar heat to enter the building. And in the summer months, they should then close to shield the building interior from high heat loads. So how do we program shading for different seasons using humidity reactive materials, which I've been talking about? So in temperate climates, such as in the southern parts of Germany, but also here in the northeast US, there's a reliable link between temperature and humidity. So taking a look at a typical winter day on the left, you can see that the humidity in blue remains quite high, while the temperature in red remains low. But on a typical summer day, there are more daily fluctuations in temperature, but the humidity always remains with this inverse relationship. And so we design our shading elements to then therefore curl and open when humid and flatten and shade when dry. And then we needed to design a material to match the response time to the time scale of weather changes in Freiburg. And so together with the material scientists, we developed a highly responsive filament material consisting of 35% cellulose content and mass ratio. We went through a very extensive testing process in the lab using an active microclimate generator to cycle many times, alternating high and low humidities, where we discovered actually that our LED adhesives were not very robust against high humidities. But also that our 4D printed materials could continue to operate against the disturbances unfazed by multiple attacks. And in order to test their performance under real weather conditions, I also built a mock-up of the facade in Stuttgart at the same height and orientation as the target building in Freiburg in order to simulate the 4D printed elements in the full range of humidity, temperature, and UV effects of Freiburg, of that type of climate, across all seasons for over a year. And then with the assurance of our extensive testing, we then rented a total of 4 3D printing machines to fabricate almost 450 shading elements. Because of that very efficient mesostructure and the fact that it's all flat, each element only took 20 minutes to produce on average. And so the entire process of 4D printing that facade took 17 days and used less than 6 kilograms of materials. And the printers were not working 24 hours a day. All of the 4D printed elements were then pre-assembled at our lab onto thin aluminum strips through this integrated 3D printed press fit connection. And after each window was then pre-assembled, they went through a short testing cycle again, just to make sure that there's no defect before the installation. In the end, we had these 8 pre-assembled windows, and the 4D printed elements are very lightweight. So these very lightweight windows could be packed up into one minivan, driven to the construction site, and just unloaded by myself and my assistant, and simply installed from the roof without any cranes or any heavy machinery or equipment. So we designed this window system with operable glass doors, which allowed us to access that window box cavity for installation and repair or removal if needed one day. And I also want to mention that the window box frame is also vented on the top and the bottom, which allows those 4D printed shading elements to equalize with the outdoor temperature and humidity. And there are also sensors to keep track of the conditions and a camera to track the shape change of those windows. So that's, here it is in real life. And this is, to my knowledge, the first 4D printed weather responsive adaptive facade, which is also a real building. And I'm proud to say that it's open to the public, and it's also used by students, researchers, and faculty at the University of Freiburg. So this is just a couple days after installation. Very happy to see those shading elements work immediately. So you can see in the morning, when it's cold, it starts to shade when the afternoon heats up. And just as a small kind of side note, the electronics inside the windows, like the tracking, the sensor tracking and monitoring, actually took more than a year to get working. So I think that speaks to the robustness and the simplicity of such a material system. This is the view from the inside. And yeah, I think the feedback that I've gotten is that it's really interesting to be inside of a building that's sort of moving on its own, but I think for a lot of the feedback I got, it was very positive. So this bio-inspired facade, I just want to kind of end here and say that it requires zero energy to operate, right? It demonstrates that resilience against things like power outages or the complex engineering and constant maintenance that's required for comparable electrical mechanical systems. The solution also has the potential to be scalable. So we showed that we were able to scale up the process of the 4D printing production to the scale of an entire building facade. And we also were able to just use commonly available 3D printing equipment, fused filament fabrication printers, which are very widely available, and also the most abundant biopolymer on Earth, which is cellulose. So, yeah, I would very much like to completely get rid of the aluminum that's in the frame and also the steel and the structure one day. So looking beyond facades, in a project that was recently awarded by the EU, we'll be looking at using monomaterial systems in a collaboration with material scientists and physicists. So we're hoping to use recyclable and develop biodegradable materials that are both load-bearing and shape-changing. And there are still so many lessons to be learned from nature. So how can natural materials be sustainable yet performative? And that's the overall mission of my research and what I'll be continuing to do here at Cornell University, to pinpoint how we can harness the inherent characteristics of natural materials to perform even more advanced functions. And I hope to showcase bio-inspired design and making as a credible pathway to overcoming the competing resources between nature and technology towards a future where our technologies are no different from nature. So I'm looking forward to hearing your thoughts. Thank you very much for your attention.
Hi, good evening, Ms. Chen. Thank you so much for coming, and my name is Louis, one of the BArch student here at Cornell. I just think everything that you're doing is incredibly exciting and very innovative and boundary pushing. My question to you is, when you're doing the 4D printing, unlike traditional 3D printing where it requires kind of like heating up the filament and then kind of like inject the filament into the nozzle and do the actual printing, with your 4D printing with like these organic infill that you were talking about, how is that like operational wise?
Yeah, that's a really good question. So actually we are developing, we're actually using off-the-shelf thermoplastic materials as well that are infused with wood, so up to 40% recycled wood or other types of natural fibers. We also have developed our own material, like a filament material that is specifically designed to be responsive and using a bio-based material. So actually, it does go through that heating process, as you say. It's using conventional fused filament fabrication technology. You can also print without heat using paste materials. It's slightly different, but yeah, so it's actually compatible with a normal printing process.
That's so cool. Thank you so much.
Hi, my name is Kyra, and I'm from the engineering school, actually, so I study bioengineering. I thought this was all very, very cool, and I think much needed in this world in terms of sustainability. So I guess my question is, like, in the same way that when you use a rubber band too much, it can stretch out, is it similar with this material, and is there a way that if the material is, like, a bit torn apart or, like, damaged, like, can it self-repair?
Yeah, really good question. So in this example with the facade, actually we've tested we've tested up to 200 cycles before installing it into the building. And now in the building, it's been there for, well, one of our prototypes has been outside for almost 3 years now. So there's a limit to how many cycles we can test because of the time it takes for the climate to basically be controlled or be saturated with humid or dry air. So, but we're hoping with this project we can actually do that long-term testing. And also about the robustness of the system, actually, with those operable doors on the facade, I had thought that I would have to go up to the roof and fix it from time to time. And the only thing that I've had to fix were actually the electronics for the sensing, which is kind of funny. And so yeah, we really designed this so that it would be easy to repair, but we haven't had to repair any of them yet. We have done a lot of testing to make sure it doesn't delaminate. So far, there is no delamination. And I think a part of it is also the redundancy of the system. So that also helps. If one part of this flap or this element breaks, the rest of the material can also continue to operate. As you also saw in the one with the LED falling, like they're actually really robust to mechanical disturbances.
Thank you.
Hi, Professor Cheng, this is Dana. I have questions about when you mentioned when you copy inspirations from biology or from nature, forces, a lot of things, materials, they don't scale just linearly or in your most expected way. So I was wondering, as you're pre-programming these materials, these kind of structures, are there new, unexpected, or emergent patterns that you've seen in your past experience?
Yeah, that's a really interesting point about the scale. So it's true that things don't often, scaling down 3D printing is difficult. Scaling up is also very difficult with a new set of challenge. So but actually with some of the systems that we have developed, I think the main, well, as an architect, I want to design things that are sort of on a larger scale, right? And I think the key is to be able to control the resolution of what you're making. So I guess with the example of the large-scale additive manufacturing setup, I think what was really nice there is we could use bulk materials or coarser materials where maybe that functionality, that high resolution isn't needed to kind of emulate certain bio-inspired behaviors. So I think the key is really to link the large scale, the low resolution fabrication to the high resolution fabrication. I hope that answers your question.
Yeah, my name is Messi from Design Tech Department. Thanks for this inspiring lecture. I'm so excited to witness it. So my question is, in your inquiry or research into nature, how do you approach it? Do you approach it in a qualitative manner or quantitative manner, or is it a mix of both?
I think it depends. That's a good question. It's really, there are a lot of different approaches to bio-inspired design. There's very systematic ways. Sometimes things you discover sort of randomly. I'm trying to think of one which was sort of a, but I mean, there are a lot of examples in history, right? Like the discovery of or like the development of Velcro was kind of a very random finding of someone walking, a Swiss inventor walking their dog and discovering this, and then, okay, looking at this hook and loop system and thinking that there could be something there. But there also have been biologists who develop very systematic approaches. So I think there's no right or wrong answer on how to do this. I guess for the pine cone research that I've been doing, this was actually based on a lot of previous research besides, like, from the sciences. There's a lot of work from many decades ago on how pine cones open, and took a lot of abstraction to get to this point.
Thank you, Professor, for the lecture. My question was related to the large-scale prototype that you guys did, the arch. Can you talk a little bit more about how was the process of creating and, I guess, putting together the recipe for the extrusion, and also relating to the question about scale, what were some of the properties that were different for that scale compared to the smaller 3D printed portions?
Yeah, that's a good question. So we did the research at the desktop scale, and we sort of discovered those relationships between the pattern density, the anisotropy of the pattern, things like that. And so when we upscaled, of course, we had to recalibrate all of that because the nozzle size is different. So there are process parameters that are completely different. So it's really hard to simulate. That's why a lot of this work is based on experimental data. As soon as you switch like the material or the manufacturing process parameters, it's just you have to it's faster to just create those experimental data. And one of the major challenges is the weight, the self-weight of the system. And also, when the structure is shaping, those loading conditions are also changing. So it's very complex when you want to scale up structures. And I think a lot of structural engineering has to come into play at that scale. But I do think that the general relationships, I mean, for example, the bilayers can also work at a large scale, but then stiffness of those, like structural depth and the resulting stiffness comes into play. But, you know, it doesn't scale linearly, and you have to develop new strategies, for example, creating more surface area on those materials to have more, to reduce or create more porosity so that the moisture can be absorbed, things like that.
We have a few questions online from Ekaterina. Her question, you mentioned that you're in the process of developing larger scale solutions that would include bearing structures or larger partitions of the buildings. If I understood correctly, could you please elaborate on that? How and why could large bearing parts of the building be in motion in your vision?
Yeah, great question. So one of the things I'm thinking about is, of course, how to replace, you know, steel and things like that in our buildings. And so there is research of buildings that, you know, buildings have to react to things like earthquake or wind loads or, you know, et cetera. So you might not see those structures moving a lot, but they do move. And so I think that for upscaling, it's not really about large movements. It's about small movements that adapt to small things like, earthquakes for one example. And in that project that I mentioned, that I'm embarking on this new collaboration with the material scientists, they developed a new material, this foam-based material, which is very lightweight. And it's also recyclable, already in recycling streams in Finland. So I think this is also a really interesting area to pursue, because a lot of the construction in our buildings, it's a layering of so many different materials that makes the reuse and the recycling of buildings really difficult.
another question online that's somewhat related. Are you doing any evaluation of the life cycle, environmental and social impacts of the bio-based materials you are using or contemplate using?
Yeah, that's a great question. So not yet up to now, but in my upcoming project, actually, we are working with a company which focuses on sustainability. So they have the ability to do life cycle assessment, and we're also really interested in how people react to such like bio-inspired structures, because it is very different from what we are used to. We're not used to our buildings moving. We're not used to the idea of our buildings being made out of bio-based materials, and there are a lot of negative connotations in that regard in some countries and communities. So that would be something that I'm interested in also, overcoming, getting people more comfortable to the idea of buildings that move, that have agency.
Hi, Tiffany. Thanks for the lecture. I maybe have a follow-up question. If you have kind of like any idea of a lifespan of such an element, and then I understand that there is the flexibility, we can produce them easily, we can exchange them, but you mentioned that a lot of the examples were actually bioinfused polymers. That means that, if I'm not mistaken, they're not recyclable. So there is the element of production of waste. Is there a way to make it fully biodegradable? Or if you can expand a bit on that. Thanks.
Yeah, great question. I think there are like so many levels to this. So yeah, we, in this example, it's actually two materials, right? So it's not recyclable. And that's something that I really want to do, is to develop monomaterial systems so that it would be much easier to grind them up and reuse them. I think everything has a lifespan. One of the things we're trying to figure out is how to be able to guarantee how long these can last and can continue to perform without any defects. So far, it doesn't seem like there's any reduction in performance, but we're still limited by, how many cycles we can test, just because of that physical limitation of controlling the climate and that. But what I will say is that I'm really optimistic. So I think creating monomaterial systems is one of those steps. But what I like, things don't last forever, right? So they have to be recyclable, or they have to biodegrade. And I'm very happy that my material scientist partner is able to create materials that can biodegrade. One of the challenges is things like fire safety and things like that, which, there's a trade-off between all these things, but I think there are steps that we can work towards, right? Like, one is just to make a monomaterial system.
Just a small follow-up, but the idea is that, because I assume also, having worked with polymers, that the assumptions that don't last as long as we would like for buildings to operate. So is that the assumption that the polymer would actually degrade faster, and then it would cease to have the motion that it should have?
So I think it depends for some things. I mean, things like parts of your building, they always need maintenance. For example, my roof lasted for, 40 years. Then we recently had to redo our roof, my parents' house. And so then, what happens to the asphalt, right, afterwards? So that's one thing. Those things don't last forever. And in anything, I think we always have to think about the lifespan, but perhaps there's a way to have our building components be, let's say, reconfigurable, like create a new purpose, right, from the materials. Maybe it degrades, but it can become something non-load bearing, or within the house. Maybe we can look to nature to find new types of mechanisms that are, let's say, I don't know. There's some wild ideas, like you can reprogram things. So I don't know. I don't really have the answer to that, but I think that would be, I think there are things that we can look to in biology for that.
Hi, thank you so much for your presentation. It was really nice. I had a question about the failure of the material. So what did you notice? So can you elaborate a little bit more on that? Was it because of extreme temperatures, or when did the structure actually start failing?
Good question. I think the failure mostly happened when the printing parameters were not very good. So delamination was one a big factor if there was some unevenness in the bed. But if those materials are, if the process parameters are good, the quality looks fine. I mean, in that facade, I haven't had to replace anything. I've been monitoring it, and there's no real reduction. So, yeah, I don't know. I mean, I would say the failure is mainly through poor manufacturing, which we are able to catch before putting into the building through several steps.
Thank you, Tiffany. I have a question about your collaborative process. When do you depart from the natural model? And I imagine that shifts depending on the project, their deadlines, et cetera. And related to that, how is your work through that collaborative process impacting the science that's being done by your collaborators?
Yeah, really great question. So I think, I mean, I can say that at my previous institute, a lot of the projects did come from a very strong biological inspiration. And then as it continues to develop, as it is moving from the lab environment to maybe the industry kind of production, prefabrication environment, sometimes you lose that just because there may be other things that you have to worry about, like fire safety or material, like the structural testing of the materials. And so with this project, actually, I had a lot of ambitions to test some new ideas of the pine cone. So one thing was the fact that there are sometimes triggers, like there are also heating overrides, like if it's hot enough, it'll close, for example. That's something that you sometimes see in pine cones. But because we needed to deliver this project in a real building, some of those ideas we had to put to the side. And I think that it just requires some, I mean, this was like 6 years of research before it got into a building. So I think there just needs to be a lot of fundamental research that can verify and you can sort of master the fabrication techniques in order to create that bio-inspired design. So yeah, I think there's a lot that we want to explore in the future about still the pine cone. There are a lot of things the biologists are just always finding new things about the pine cone. So yeah, and then the second question I think was about what fed back into biology. I think the example of the reverse biomimetics was really interesting because I didn't realize when I first kind of did this interdisciplinary research, I had the impression that the biologists knew already so much about the plants, and I realized that they're always discovering new things. So we can use our technologies to help them verify things like what is actually happening within those cross-sections of the plants. And it's not just a bilayer. It's actually way more complex than that, and we're continuing to study this. Another thing with the material science, I think with self-shaping materials, what was interesting is that they also, through that process, we developed that material, and we discovered what are the best polymer properties for a self-shaping material. So there's a lot of feedback both ways, I would say.
Great talk, Stephanie. I wanted to ask you a question that projects. So you looked at mechanical properties and forces. What other, let's say if you look from the architectural side, what other materials functions would you be interested in the future?
I think if there was a way to decouple temperature and humidity. So right now I am looking at cellulosic materials, which is just because it's one of the most common examples that we find. But there are also plants that are only responsive to temperature, or they are actually tracking the sun. And that's something like so everything is kind of pre-programmed, right? The solar tracking of sunflowers are especially interesting because it's actually following like in a non-pre-programmed path. So I think a material like that would be very interesting for, let's say, harvesting energy. Yeah, and I think pressure also. So what if we could have some materials be pressure activated to control ventilation in the buildings? That would also be sort of a wild idea, I think. But yeah, there's a lot of interesting ideas with ventilation that I would be very interested in as well. And I think pressure activated materials could be one of them.
Two last questions online, and maybe I'll couple them. The first is a technical question. Could you please explain which software you used for your simulation, especially for the auxetic structure that you mentioned for your master's thesis? If Grasshopper, did you consider FEA analysis? And then the second one, do you think the shading system is ready for industry?
Yeah, so a lot of the, well, we primarily are using Rhino 3D, and on top of that, I developed a Grasshopper plugin, or Grasshopper kind of workflow for the 4D printing. For the master's, my student's master's project, thesis project, they were using Caramba for the simulation aspect. And it's not a perfect solution, I would say, but it was good enough for being able to create that shell structure. I think with a huge difficulty with simulation is that it's just really hard to simulate, like the patterns. So there was a lot of calibration that had to happen in order to sort of program or like to model the material behavior. Yeah, so actually a lot of the things that we do is just experimental data. We have a nice workflow where we can print samples really quickly. Large scale or small scale samples can be printed 5 minutes at the small scale, about 10 minutes at the large scale. And we can use imaging to observe how it deforms. And then we use that information to basically predict how our structures will deform. And maybe this would be a really interesting application or use case for machine learning, since we're generating so much image data.
Please join me again in thanking Tiffany for a really excellent talk. Thank you.